In large-scale software projects with continuous integration pipelines, minor code changes happen hundreds of times a day. But embedded within those routine feature revisions and refactoring efforts are occasional unintentional security flaws that integrate directly into the core codebase. Catching these flaws requires just-in-time vulnerability detection, or JIT-VD. The objective of JIT-VD is to evaluate a newly submitted commit and identify if it introduces a vulnerability at the exact moment of submission, before it is merged into production. Evaluating a commit is an inherently heterogeneous task. An auditor must parse structural diffs to see what lines were altered, read the developer's commit message to understand the intended goal, and map those changes against the surrounding file-level context to gauge systemic impact. Synthesizing these overlapping layers of data creates a massive cognitive load. For human reviewers operating under strict release deadlines, reliably catching subtle logic errors across thousands of lines of contextual code is nearly impossible. Because open-source collaborative models inherently enlarge a software supply chain's attack surface, an automated JIT-VD system provides a necessary defense against the scale of modern vulnerabilities. The standard industry assumption is that modern large language models can solve this. Because models demonstrate deep code understanding, developers assume that standard zero-shot prompting, or step-by-step chain-of-thought prompting, should be enough to evaluate a commit and flag security risks. This chart shows the empirical performance of DeepSeek v3.2 using chain-of-thought reasoning on JIT-VD tasks. While the model achieves 86% precision on the commits it flags, it detects only 6% of the actual vulnerabilities present in the dataset. This failure stems from context dilution. A single-pass LLM cannot simultaneously hold structural logic, semantic developer intent, and a complex security taxonomy in its immediate working memory. When forced to weigh all these variables simultaneously, a single model either hallucinates connections or defaults to extreme conservatism, refusing to flag anything it isn't absolutely certain about. A security system that misses 94% of active vulnerabilities is functionally useless in production. Solving JIT-VD requires a distributed, coarse-to-fine multi-agent network. Distributing the cognitive load across several specialized roles addresses the limitations of monolithic reasoning. This is the operating principle behind the VIC-RAGENT architecture. Stage 0 splits the raw commit into two paths. The code analyst maps structural relationships from the diff, ignoring the message. Meanwhile, the target analyst focuses on semantics, checking if the developer's stated intent aligns with the modified files. If the target analyst finds inconsistencies, like a commit claiming a minor refactor while modifying core logic, those anomalies are flagged as early indicators of risk. By separating syntax from semantics, Stage 0 creates a clean, dual-view representation. The subsequent security analysis is no longer burdened by formatting noise or contradictory data. The structural and semantic views converge at Stage 1. Here, the vulnerability inspector focuses on preliminary candidate generation, gathering a broad set of hypotheses. The inspector evaluates the data against predefined categories, searching for signatures of memory safety, threats to web security, flaws in resource management, and I/O validation. Stage 1 intentionally relaxes verification constraints. The agent's temperature is raised to 0.4, creating a high recall net to hypothesize risky patterns, even with incomplete evidence. Vulnerability-inducing commits are subtle and rarely exhibit explicit violations initially. Stage 1 captures a massive superset of potential threats, ensuring suspicious fragments are recorded. By optimizing for candidate generation over immediate precision, this bypasses the conservative bottleneck causing models to miss 94% of vulnerabilities. The output from Stage 1 is a large, noisy pile of hypothesized vulnerabilities. Stage 2 filters that noise by applying strict contextual constraints. The vulnerability inspector reevaluates each flagged fragment, reasoning strictly against its predicted vulnerability category. This type-guided reanalysis aggressively narrows the reasoning space. To evaluate borderline cases, the system uses retrieval-augmented generation. It encodes the commit into a vector and scans the vulnerability knowledge base, injecting matching historical cases as hard evidence. Ablation testing confirms the utility of this step. Without Stage 2, true positive detections drop and false negatives rise. Without historical context, the LLM fails to disambiguate complex code changes. Stage 2 converts uncertain hypotheses into evidence-backed theories, maintaining high recall while reintroducing logical rigor. Before issuing a system-wide security alert, the framework passes the refined candidates through a final bottleneck to eliminate the remaining generative uncertainty. The vulnerability inspector's temperature is dropped to 0.1, forcing an incredibly deterministic verification that strips away lingering hallucinations. The system then applies a strict commit-level aggregation rule. The commit is classified as vulnerable if even one fragment survives this final gauntlet. This bottleneck is highly necessary. If Stage 3 is disabled, false alarms spike by nearly 40%. In a live enterprise pipeline, excessive false positives generate alert fatigue, leading developers to ignore the security auditor entirely. Stage 3 trades a negligible fraction of recall to aggressively prune false positives. When a vulnerability is verified, a document specialist generates a report, feeding it back into the RAG database, ensuring the framework continuously improves. From structural extraction to candidate generation to strict verification, VIC-RAGENT operates as a unified coarse-to-fine filtering machine. This chart compares the final performance metrics running on DeepSeek v3.2. VIC-RAGENT achieves an F1 score of 57% and 48% recall. This drastically outperforms the 16% F1 score of direct prompting and the 11% F1 score of chain of thought. To verify that the multi-agent system is actually reasoning and not just recalling memorized training data, researchers tested VIC-RAGENT against newly disclosed common vulnerabilities and exposures, published in late 2025 and early 2026, dates explicitly beyond the underlying model's training cutoff. On these previously unseen vulnerabilities, VIC-RAGENT maintained its lead, outpacing standard agent frameworks in both recall and precision. It logically deduced the presence of novel flaws, using its constrained verification rules. These metrics prove that explicit role decomposition and multi-stage constraints solve the specific weaknesses of monolithic reasoning. Modern large language models possess a staggering understanding of syntax, but auditing a commit requires analyzing intent, historical precedent, and structural impact. That level of complexity cannot be resolved in a single computational breath. Orchestrating an expanding phase of candidate generation, followed by a contracting phase of strict verification, allows foundation models to manage these overwhelming security tasks. This coarse-to-fine agentic blueprint offers a practical, scalable solution for continuous integration and DevSecOps pipelines. Ultimately, architecting a synchronized team of specialized agents allows software security systems to handle the specific complexities inherent in the development lifecycle. In the next era of automated software security, true intelligence doesn't come from a bigger monolithic brain, but from a perfectly synchronized team of agents.